Fusion energy, often touted as the holy grail of clean energy solutions, holds the promise of providing a nearly limitless, clean and safe energy source. This process, which powers the Sun and other stars, is based on the principles of nuclear fusion, a reaction where two light atomic nuclei combine to form a heavier nucleus, releasing a tremendous amount of energy in the process. At the core of the Sun, fusion occurs under extreme conditions of high temperature and pressure, allowing hydrogen atoms to overcome their natural repulsive forces. When these atoms collide at high speeds, they fuse to form helium, releasing energy in the form of photons. This energy travels to the Sun's surface and then radiates into space, including towards Earth, providing the light and warmth that sustain life. The challenge on Earth is to replicate these extreme conditions in a controlled and sustained manner. Fusion research primarily focuses on two isotopes of hydrogen, deuterium and tritium. When these isotopes fuse, they produce a helium atom, a neutron, and a significant amount of energy. Two main approaches are being explored to achieve controlled fusion: magnetic confinement and inertial confinement. Magnetic confinement, used in devices like tokamaks and stellarators, involves using powerful magnetic fields to contain the hot plasma, a state of matter where atoms are ionized, in which fusion occurs. Inertial confinement, on the other hand, involves using lasers or ion beams to compress fuel pellets to high densities, initiating fusion. The path to practical fusion energy is fraught with technical and scientific challenges. One of the biggest hurdles is achieving a state where the fusion reaction produces more energy than is consumed in initiating and sustaining it, a milestone known as net energy gain. Containment of the extremely high temperature plasma is another challenge. The plasma must be maintained at temperatures exceeding 100 million degrees Celsius, much hotter than the core of the Sun. Materials that can withstand such conditions without degrading are yet to be fully developed. Another challenge is the handling of neutrons produced during the fusion reaction. These neutrons can weaken and activate the materials they collide with, raising concerns about material integrity and radioactive waste, albeit much less than in traditional nuclear fission reactors. The future of fusion energy is potentially revolutionary. If these challenges are overcome, fusion could provide a nearly inexhaustible energy source with fuel derived from water and lithium. It's inherently safe, with no possibility of a meltdown and minimal long-lived radioactive waste, addressing key concerns associated with current nuclear fission reactors. Fusion energy could drastically reduce our dependence on fossil fuels, helping to mitigate climate change by providing a large-scale, low-carbon energy source. Its widespread adoption could lead to significant shifts in global energy landscapes, impacting everything from geopolitics to economic structures. The field of fusion research is continuously evolving, with several promising technologies. Advanced tokamaks are being designed to improve plasma containment and stability. The International Thermonuclear Experimental Reactor Project, an international collaboration, is currently constructing a tokamak in France to demonstrate the feasibility of fusion as a large-scale energy source. Alternative approaches like using high-temperature superconductors for stronger magnetic fields or exploring different fusion reactions are also being pursued. Research into laser-driven fusion and other inertial confinement methods continues, aiming to achieve more efficient ignition of the fusion fuel. In conclusion, fusion energy, mirroring the processes of the Sun, stands as a beacon of hope in the quest for clean and sustainable energy. While the challenges in making this a reality are significant, the ongoing research and technological advancements bring us closer to harnessing this potentially transformative energy source. The successful development of fusion energy could herald a new era in human history, profoundly impacting our environment, society, and the future of our planet.